Right, I know, I interrupted.
No, that's okay. That's okay. Take one of those and pass them around. Bringing this up.
I was hoping you were going to print those.
Okay, guys, so any other assignments are due 3 minutes ago. So if you have it, give it up now or forever hold on to peace. All right, so what I wanted to do today was I wanted to go through and start talking about digital logic circuits and different number bases. And I think that we also had one more example to do with the rules of inference as well. So let me pull that up as well so that we can finish that up. Because I think I'm going to ask for you guys to submit that on the next assignment. Let me do that. So I think we did the first one, correct? And we just didn't do the second one. Okay. So sorry, it's been a week and I forgot where we were with regard to that. So okay. That's what. No. Okay. So let me copy this down real quick while you guys are still getting the worksheets. Not W. Yes, sir.
Did you need to hand out 2 different sets of notes?
Is there two?
Yeah, I got.
I didn't realize it was for two. I thought it was just one.
Oh, what else do you have? Oh, statistics stuff.
Found that one.
Measures of central tendency.
Yeah, that's statistics. Just hand me back the statistics stuff. Sorry about that. I didn't realize that they were lumped together. I just got it back from the copy. So I was wondering where we were.
Has them up in front and center.
Sorry about
You should
that.
have digital logic circuits.
That's fine. Yeah, if you guys want, just pass all the extra stuff up and whatever, or you just pass it down to the end. I don't care. So I actually made extra copies of them this morning because I couldn't find them, and they were just lumped in with all the other stuff. Okay. Okay, guys. So let's go ahead and see if we can do this other example of showing that an argument form is either valid or invalid, and we're going to use those rules of inference. Okay. So go ahead and bring back up that worksheet that has the rules of inference at the bottom. All right, I'll try to bring it up on the screen so that way you have it. It's the one that has the Boolean logic laws on it. Okay. So these are basically like our 8 rules that we can utilize. Remember what we're trying to do is we're trying to put together some sort of, I guess, I wouldn't say roadmap, but we're trying to put together like an algorithm, if you would, that's going to lead us to the conclusion. Okay? So I think that's last time what I suggested was you always start with the most simplistic possible statement that you have and then try to work from there. Okay? So to me it looks like not W is the most simplistic statement. So we're going to start with this, okay, just because it only has a singular statement in there. And then what we want to do is we want to look at something else that might have a W in it. Okay? So always start with whatever has just one term in it or one statement. And then it looks like to me that the only thing that's possible that has one statement is U or W. Okay? So let's see if we can build one of those 8 basic rules of inference, maybe just using these 2 statements. Okay? So does somebody think they might be able to put together a statement and then come up with a conclusion from that argument form? So, go ahead, sir.
So U or W, and then not W, so you have U.
Okay, so we would have U or W. That's given. Not W is also given. And therefore you ended up with U, correct, sir?
Yes.
Okay. Now, what was one of the 8 reasons that you were able to give that, sir?
Elimination.
Elimination. Good. Okay. So this is valid by the elimination property. so make sure when you guys are doing this, you justify your steps, okay? So that's the elimination step. All right. Once we're done with that, what we can do is we can usually just cross these off, and then we can look for something else that might have a U in it, okay? So it looks like that the only thing that might have a U in it is the third statement form, okay? So does somebody think they might be able to use what we just got in step 1, as well as something else in the given information, to try to come up with something conclusion or some conclusion for the next step?
So U implies not P.
Okay, so we have U implies not P. Yes, sir?
So not P.
Not P.
Not P implies RNS.
Well, we don't want to use, we don't necessarily know not P yet. Okay, so we can't use that. So, suggestions, sir?
Could you do like U therefore not P?
So we could say, we have U from step 2, therefore not P, okay? All right, the first step was given. The second is a result of step 1. We just showed that's true because we know that all those rules of inference are indeed valid, okay? So U implies not P. U is valid by step 1. And then which of the 8 rules is going to be able to enable us to go and say that this statement or this argument
Modus
form is valid?
ponens.
Modus ponens. Very good. Okay. Okay. So does that make sense, guys? All we're trying to do is we're just trying to build something that looks like those basic rules of inference. Okay? We can cross out U implies P now, or U implies not P. And now, at this point, we have U and not P to work with, okay? So does somebody think they might know a next step that we can utilize to be able to try to continue with this?
Not P. Then not P implies RNS.
So we have not P implies R and
Not S. Sorry.
Okay, that's okay. Okay, so I like using that one, okay? And then what else could we use from there? Or what else could we do? Yeah, we could use not P, and we had not P from step number 2, right, Don? Good.
Yep.
So that's going to be not P from step 2. And then what's that going to result in, and why?
R and S.
R and not S.
R and not,
That's
not S.
okay.
Sorry.
Good. So R and not S. And why are we allowed to say that we can conclude R and not S?
Modus ponens.
Yeah, modus ponens again, okay? There's no law saying that we can't reuse the same laws, okay? So this is valid by modus ponens. Okay, good. All right, we can cross this one off. Now remember, we're trying to get to not T, okay? That's the conclusion. So now what we have is we have both R and not S at our disposal, okay? So I think we're basically 2 steps away from being able to get to the answer to this, or to the not T that we need, okay? So, for step 4, okay, if I look at T implies S, which is the only premise that we have left, excuse me, wouldn't I want to use something with an S in it?
Mm-hmm.
So from step 3, I'm given R and not S, okay, that's step 3. Well, what can I say that might be useful as a result of having both R and not S? Sir?
Implies not S.
Yeah, because it's going to be the specialization, right? We just choose one of the 2, okay? If I have, I don't know, blue marker and black marker, I have them both. So I just pick the marker that I want to use. So this is going to be valid, not S, or therefore not S, by the specialization rule. Okay. So, and the reason we knew to use not, or that we knew not S was going to be useful, is because there's no R in any of the other premises, right? You just want to pick the one that we need from this. Okay? So if you have an and, you can do that. You can't do that with an or. Okay? And then finally, for step 5, I think we can finish this off. So does somebody think they might be able to get to the conclusion given the information that we have thus far? So, go ahead, sir, please.
Can you use modus tollens, say T implies S?
Yes, sir.
Not S, therefore T.
Perfect, thank you, sir. Therefore, not T. So not S was for, that's okay, you're fine. Don't worry about it. I knew you'd write it as that. From step 4, you had not S, and then as a result of modus ponens this time. Okay.
Told
I'm
Tollens.
I'm sorry, that's right, we used ponens in the other ones. I apologize, I got the first word right. But as a result of modus tollens this time, then we get to not T. Okay? Alright, so this is exactly what I would ask you guys to do for homework. Okay, so this is like those last 2 problems that were on assignment 1. So you guys will just hand those in on, I guess, next week when you guys submit the assignment. Okay, I think the next assignment is going to be due next Wednesday. Okay, so that way you guys have a few days to work on that stuff and also answer some questions.
On the 14th?
One more time, sir?
On the 14th?
Yeah, today's the 7th, so yeah, the 14th. Okay, I'll post it in Blackboard, so I just haven't thought that far in advance. So. Okay, all right. Questions I can answer, guys, about this. Okay, usually what I do on the first examination, I give you guys a question just like this. It's worth 10 points. Okay, so make sure you guys go back. If you don't understand it, make sure you guys come and see me so I can help you. Okay. So the next section that we're going to take a look at is we're going to start taking a look at the circuits, the digital logic circuits, and different number bases. Most students do very well with this stuff. Okay, so remember we just talked about truth tables, we talked about truth values, inputs, and outputs. Okay, one of the applications of that is something called a digital logic circuit. Okay, every computer is comprised of billions of circuits, and when it comes down to the core, every computer circuit is designed with either an and, an or a not, or several of those conjoined together. Okay? Some of you guys might have worked on breadboards, some of you guys might have done some computer architecture where you actually program those sorts of things in, and you might put like the different conductors together, the logic gates together to be able to figure something out like that. Some of you guys may have not done that. Okay? So I don't really care if you have or haven't, doesn't matter. All we're going to do in this class is just look at those. Okay? So, with a digital logic circuit, okay, once a signal goes through it, you can't reuse the signal. In other words, you can't backtrack a signal, okay? A signal's one way. You can loop it back around if you wanted to for some reason, like if you wanted to do this, but that wouldn't be smart because then you never really have an output. You just have you just have basically an infinite loop, and that's not going to do anything for you, okay? So when I say that there's only one output, what I mean by that is that once it goes out, it shouldn't be going back into the same circuit for any reason. Okay? Alright, there's only a finite number of inputs. And that's just because if there were an infinite number of inputs, that means there's an infinite number of material. That doesn't matter. Okay? The only possible inputs are true and false. Okay? You can't have like a 2 being pushed through here. When we start talking about digital logic circuits, instead of true we use 1, which means valid, and then for those of you guys that know computer science, 1 is like the Boolean true, and then 0 is the Boolean false, okay? So that's basically the inputs that we're going to be putting through this, okay? So does that make sense, guys? The only things that go through circuits are 1s and 0s, nothing else. No cats, no dogs, no lawnmowers. All right. So one of the most basic things that we have to do is we have to make sure that if I give you a circuit, you know all the different combinations and permutations that can come out of that circuit. Okay, that's basically fundamental to this. Okay, so we have this circuit, and the first thing I want to do is I just want to make an input-output table for this circuit. Okay, when I say input-output table, it's the same thing as a truth table. Okay, so here's what we're going to do. We're going to have a P. We're going to have a Q. Because we have a P and a Q, how many rows are we going to have for this input-output table? 4, right guys? 2 to the 4, or 2 squared is 4, okay? And basically, remember how we did true, true, false, false, true, false, true, false? Well, now what we're going to do is we're going to do 1, 1, 0, 0, 1, 0, 1, 0. Okay? If you want to use T's and F's, that's fine for me. Okay, but if some of your teachers might not like T's and F's, if you're in computer classes, they might want 1s and 0s. Okay, so just don't use T's and F's. Make sure you ask your teacher. Okay, I know the difference, but they might not. Okay, So here's what we're going to do, guys. We're going to have an output for this. So we have two trues going through there. Okay? So here's the way that I think about this. Okay? Let's say I run 2 1s through that table. Okay? Notice that this P right here just kind of carries down. In fact, let me do this. Let me put the 1s at the beginning. Not that it matters that much, but so there's 2 1s that are being run. So in other words, whoever's running the circuit turns on the impulses. Okay, so there's 2 electrical impulses that are going through there at the same time. This 1 actually traces down to here. Okay, so all we're going to do is we're just going to figure out what's going to happen. Okay, if I throw a 1 and a 1 through a gate, what's the output of 1 and 1?
1.
1, right, guys? If it's true and true, just like you guys did with Boolean stuff, okay, or when we did with the truth tables, it's a 1. Okay. What happens if I run a 1 or a 1 through this?
1.
That's a 1 as well, right? Remember, the only time an or a disjunction is false is when you have both zeros. What happens when you run a 1 through a not? It's a 0, right? So basically what we're saying is that if I run 2 1s through that gate, in other words, I turn both impulses on, the output is a 0. Okay. Does that make sense, guys? We're just basically tracing it, and we're using the tables that we already know. Okay, that's all we're doing with this. Okay. Now what I'm going to do, okay, I'm going to erase this stuff. Okay, where you guys can just scratch it out, whatever. Okay. Now I'm going to throw the second permutation through. So I'm going to turn on the P impulse, but I'm going to turn off the Q impulse. Okay. P still traces down, so this is a 1. Okay. So what happens when you run a 1 and a 0 through an AND?
0.
That's a 0, right? If you run 0 or 1 through here, that's a 1, and then a 1 through a not is a 0. So it looks like that, so far, all the impulses are nothing thus far. Okay. Now, let's see what happens when we run a 0, 1 through there. Okay, let's see if we get the same result. So this is going to be 0, 1, which is the third permutation. You guys already told me that as long as one of these is false, an AND is false, this 0 runs through the P. Okay. So this time when I run 0, 0 through OR, since neither of them are true, you have false or false, you have to pick false, and a 0 through a not gate negates it to a 1. Okay, so now we finally get some sort of output that has an impulse turned on for this. Okay, we could do the exact same thing with the last ones. Okay, so this time I'm just running a 0 through. Okay, and I think it's going to work out to be the exact same thing, right, guys, for that as the previous. A 0 and a 0 gives a 0. Trace the 0 through, the OR through the 0 is a 0, and then the output's a 1 for this. Okay? So, this is the most fundamental thing that we have to make sure that we can do with circuits. Okay? You basically have to know what the circuit's going to do. If you don't know what the circuit's going to do, why even try to build anything with it? Okay? Does that make sense, guys? Any questions? Ma'am, please.
Actually, the diagram with the P and the Q and the way that it is, that part doesn't kind of make sense. So is a P and Q going into AND?
That's correct.
P and Q going into OR?
What's happening is these two right here, the zeros are going through the AND. And see this, since this was initially a 0, this 0 is also following this impulse as well. So what's happening with this?
So I guess I understand the logic, but I don't understand the diagram. So is P and Q, are they both going into OR as well?
Like
Yeah, that
you're
goes-
going down too.
No, it's not connected from.
Oh no, this is just connected at the P. Okay?
Yeah.
So it has nothing to do with the Q. So it might be helpful if it looked like that, where there's just a dot where it's soldered onto that first
Yeah, I get
part.
it.
Okay, does that help now? Okay, so basically, because I can't draw it in 3 dimensions, I could have drawn it, I guess, like to go out that way. It's really easier. Does that make sense now, ma'am? Okay.
You can kind of see it in the second diagram.
Right, yeah, I did a better job on that one.
The Q.
Yeah, this one's directly connected to that. Okay, so sorry about that. I'm not trying to confuse you guys, at least not on purpose. Okay. All right. So what I'd like for you guys to do, if you haven't done it already, go ahead and take a few minutes and see if you guys can come up with the input out to the table for the second of these. Okay. So this is the first question I'm going to ask you guys to do on assignment number 2. So now's a good chance for you guys to get some practice. Okay. And while you guys are doing that, I'll try to pull up an application as to why we even care about this stuff. Yes, sir.
How
Please.
come P has just 2 1s and 2 0s instead of 4 1s and 4 0s?
Because there's only 2 inputs for the entire thing.
Oh, okay.
If it was a P, Q, and then an R, then you would have 8 rows. Okay. And you know what? Even if you did that, you still get the same. You still get the same results. You just have double the results. Okay. So you basically duplicating something. Does that make sense, sir?
Yeah.
Okay. Good. Because remember, it's always 2 to however many power of however many inputs you have, or in this case, however many basic statements you have. Okay. Good question. Because most of the stuff we've had has 8 in it. I'll give you guys another minute to finish up and then we'll go through the answer. Okay guys, so let's go through the solution to this to make sure that we're all okay with this. Alright. When I do this, okay, just for efficiency, and eventually for some of you guys that aren't too good with this, you'll get to like seeing this after doing repetition. I always look for obvious cases of things that don't work. Okay, then I go for other stuff that I think might work. Okay? Guys, isn't it pretty obvious that this is connected with an AND? If this guy's a 0, isn't the whole thing false no matter what? So what combination would give us, or what permutation, excuse me, would give us a 0 as the output automatically without doing much thought? 0, 0, right? Because guys, if you put a 0, 0 through here, it doesn't even matter about this garbage. 0, 0 gives a 0 here, which means that this is going to be a 0 no matter what. Okay, so that makes things really easy for us. Okay, so at least we're cut down at least 25% of our stuff. Okay, but if you don't see that right away, not a big deal. You can still bully it and get what you want out of it. Okay. If I put 2 1s through the gate, now from now on, I know no matter what I put through here, it's always going to be a 1 for the other 3 of those inputs, right guys? Because at least as long as one of them's a 1, then this is going to be a 1. So if I throw 2 1s through here, 1 and 1 is 1, we get a knot of 0, 1 and 0 is a 0. Correct, guys? Okay. Now, the good news is when I start throwing either a 1 or a 0 through there, that's when we're going to start getting the 1s as the output for this, okay? Because if I put a 1 and a 0 through this, that's going to be a 0. A 0 negated is a 1. And remember, this is always, no matter what we do, whether it's 1, 0, 0, 1, or 1, 1, that's always going to give us an output of 1 no matter what. Okay? So it looks like that if you put a 1, 0 through, it's going to end up being a 1. And wouldn't it be true is if I flip those around and got 0, 1, then it would also be a 1. Okay? This is a specific type of circuit that some of you guys might already know the name of this thing. Okay? Does anybody know what type of circuit this is actually called? Okay. This is something called an exclusive OR. Okay? So this guy right here, or girl, don't want to be gender biased. This is an exclusive OR. Okay? An exclusive OR means that the only way that you get an output is if you have one of them false, one of them true, okay? This circuit is actually used quite often when you're building breadboards or building other things in the computer, okay? Because you don't want both, you want basically to say, if they're the same input, whether the impulses are on or off, I want that to be false. The only time I want it to be true is if one of them is true, okay? Usually in computer science, I see this as the exclusive OR. Okay. So, for those of you guys that are going to take like a secondary course, and most of you guys probably are in computer architecture, you might see this where there's a line behind it, okay? That's actually the shorthand for writing an exclusive OR. Okay? And believe it or not, they actually make circuits that are condensed versions of these things, just to make it easier because they're so frequently used, okay? Like for instance, you guys remember the number 2.71819 da-da-da-da-da? That's what number? E, right? But we don't write 2.71819, right? We write E because it's convenient. It's the same thing. It's just more convenient to write all this garbage as this. Okay? All right. Let me show you guys like why you would ever want to know anything about a logic gate. Okay? So I found these pictures on the, and you guys don't see these for any reason. Some of you guys might have worked with something called a half adder, and some of you guys might have worked with something called a full adder. Okay? When a computer, and we're going to see this later, it might not be today, but it might be on Monday. But when a computer does operations, okay, remember, computers only work on ones and zeros, only ons and offs. It doesn't know anything else, okay? So if a computer wants to add two numbers, it goes to binary, right guys? And the binary, what happens is that it uses an exclusive OR for the sum when you add two binary numbers, and then it uses a carry for the output. Okay? So like for instance, okay, let's say for some reason, and this is in binary, okay, if I add two ones together in binary, that's not two, right, because binary only has ones and zeros. Does anybody know what the output for 1 plus 1 is in binary?
1 0.
1 0, right? Okay, so there's a carry. So 1 is the sum, and 0 is the carry, right? Well, what happens is, when you throw this through, okay, you throw a 1 and a 1 through an exclusive OR, okay, so that's sum, they might have flipped that around. Oh, I'm sorry, I flipped these around. So this is the carry and the sum. I'm sorry, I dyslexiated it. So, sorry. This is the carry, and then this is the sum. Okay, because obviously you carry over. So let's say for some reason you guys threw a 1, 1 through a half adder. 1 or 1, or 1 or 1, and gives you the exclusive OR of 0. Okay, so this would be a 0. But if you throw a 1, 1 through a half adder, that's a 1. So in binary, when a computer adds 2 bits, and remember, or 2 impulses if you would, that's how it gets 1. That's how a computer understands addition. Now that's only 2 bits, right? We want the computer to be much more efficient, which is why we go from half adders, which is just this part, and if you guys notice, the full adder is actually comprised of these 2 components right here, okay? So, half adders help us to comprise the full adder. And what a full adder does is it actually adds 2 binary numbers together, okay? So, and just think about this. This thing's ugly, okay? Like if I asked you guys to compute an input-output table for this, you guys could do it, right? I mean, you'd sit there for about maybe 5 or 10 minutes. That'd be a pain in the ass, but you guys would do it, right? But that's what the computer has to do. Now think about this. It only adds 2 numbers at a time. How many things does a computer do at once? Like when you guys are playing any sort of computer games, it does trillions per millisecond, right? Think about how much that would have to do for us. I mean, it would take us 5 minutes just to construct an input-output table for this. Think about running that trillions of times. Isn't that just amazing? I mean, that is to me. I know I'm all happy about it, sorry. But it's just amazing to me how a computer can run things so much quicker than us, okay? And when I say us, I mean human beings. Now, what can a computer do? A computer can't think logically, at least to some extent, okay? Like they have artificial intelligence, and then they do the Turing test and all that crap, but that's different, okay? So to me, it's just really cool. So anyway, bottom line is, I'm sorry, before I start going off on like some euphoric tangent, that these things are really applicable. They happen in real life Every single one of you uses this every day. You turn on a light, you use a half adder. You start your car, you look at your internet, okay? It's all half adders at some point. Okay, so I just want to make you guys aware that this stuff is used somewhere in real life. Okay, so blah, 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 blah. All right, one of the things that we want to make sure of is that if we have a Boolean circuit, okay, I like to be able to construct there's three things that we can think of with Boolean circuits, okay, so, or three different forms. And you guys don't have to write this down, because we're going to see it no matter what. We have a circuit representation, we have a table representation, but then we also have a Boolean expression representation. There's three different ways that we can express Boolean circuits, or three different conversions, if you would. So there's circuits, there's tables, and then there's the expressions. Okay. We can go from any one of these at any time. In fact, that's what we're going to be focusing on for most of today. If I give you a circuit, you should be able to construct a table and construct an expression. If I give you an expression, you should be able to construct a table and construct a circuit, okay? So that's what we're going to work on today, is converting back and forth between the three different ways that we can express a circuit. Okay, so let's go ahead and construct a Boolean circuit or Boolean expression for each of the above. Okay, so I'm going to go back up. I'm just going to put them on the board so that way it's easy for you guys to see. And then I'm going to erase all my hieroglyphics up here. Okay. The way that I think about this is I think of order of operations. I start from left to right, okay, and if there's any parentheses per se, that's how I do it. Okay, so the first thing I see is I see a P and a Q. I'm going to write P and Q, okay, I don't think I can go wrong with that. And what I'm going to do is I'm going to put that in parentheses. Okay. The next thing I see after the and is I see an or that's connected to a P. So I'm going to say P and Q, or P, and then I'm going to put that in parentheses. And then the last thing that I see is I see a NOT gate. So finally what I'm going to do is I'm just going to put a NOT at the end here. Okay. Now, one of the things you guys, and by the way, if you gave me that, that's perfectly fine. But I want you guys to take a look at those Boolean laws that we looked at that you needed for homework. Okay? I bet you we can simplify this circuit. Because sometimes what happens is we get circuits and they're not always the most efficient circuits. Okay? Look inside the parentheses, guys. Okay? Is there anything that I can do to simplify what's in the parentheses? Oh, I see what you mean, like factor it almost. Unfortunately, I think you might be on the right track, Don. Okay, so say it one more time. Maybe I just didn't understand.
Can you take out the piece on both things?
Okay, unfortunately not. That's if you had like two sets of parentheses. Could you factor the P out? Okay, sir.
The absorption law?
You can actually use the absorption law. Okay, I think does the absorption law have the P first and then the Q?
Yeah.
So actually, what we could do is we could flip these around. Okay, so this is fine, by the way, guys. But notice that if you flip around the order by using a commutative law, doesn't this turn into not P? And that's just by using the absorption law. Take a look at the truth table, guys. Doesn't the truth table say that when P is true, the output is false? Doesn't the truth table say that when P is false, the output is true? So really, guys, does it matter what Q is in this example?
Nope.
Doesn't matter, right? If we were somebody that's in the government, well, let me rephrase that. If we were somebody that we worked for our own independent company, if we work for the government, we make this thing ridiculously, impossibly big, so that way we can get spending for the next year. That's what we really do, okay? But if I owned my own company and I wanted to make a better, more efficient, cheaper circuit with less of these logic gates, I would use my Boolean rules to simplify it, okay? Isn't it much cheaper for me to have a circuit instead of having all this crap instead of having all that crap, wouldn't it just be easier for me to have this? Those two circuits are exactly the same. Don't need a Q. Don't even care what Q is. Somebody could be firing a Q into the computer, just let it do whatever it wants in the computer. Just have a resistor in there, okay? So it eats up the impedance, okay? Doesn't matter. So, this is why Boolean algebra can be used in real life, okay? Now, obviously, most circuits are much, much more complex than this, okay? That's why they hire teams of people to do this algorithm analysis.
Is that not inside the triangle?
Oh yeah, anytime you have a triangle, it's a knot, no matter what, okay? So if you have like this guy, it's an and. So I know it looks like crap, sorry, this stupid marker. Okay. Actually, it's my handwriting, I can't blame the marker. Okay. Does that make sense, guys, as to how to build a Boolean circuit? You just start from left to right, and you just go for it, okay? Let's do the second one together, just to make sure we're on the same page with this. Okay, so I'm going to erase all my crap here. Or at least I'm going to try to. Come on, magic marker. Let's go. There we go. Okay. So if I was to build, now I need a real eraser. If I was to try to build a Boolean circuit from this, okay, or a Boolean expression from this circuit, the first thing I do is I see a P or a Q. Okay, so I see P or Q. Put that in parentheses. Okay. I also see, the next thing I see is a P and a Q. So what I'm going to do off to the side of that is I'm going to have a P and a Q, and I'm going to put that in parentheses. Okay. And then there's a couple more things I need from this. So what's the next thing I might do to build this circuit or build this expression? I need a not in front of this one, right, sir? Very nice. Because guys, doesn't it say once it goes through the and, I negate it? So this is going to be a not right here. Okay. And then finally, guys, I need one more thing to finish this off. Yeah, we need an and, right? Look at the very last thing that we have on the right. That's an and. So I'm just going to run an and through this. Okay. This is an example of a circuit that we can't really do anything to simplify. Okay. I know what some of you guys are thinking. Let's use De Morgan's law and just go ahead and do a double not. Okay. So we can go ahead and write this as P or Q and not P or not Q. But once you get there, you can't do anything with that, okay? Because you can't really factor out a P because these aren't the same, and you can't factor out a Q because the Q's aren't the same. There's actually 4 unique different statements going on here. In fact, if you guys were trying to build the cheapest circuit, which one would be cheaper? The one without De Morgan's law or the one with De Morgan's law? Without, right? Because doesn't this one need 2 knots, and this one only needs 1, okay? So, sometimes the Boolean algebra is good. In this instance, it's not so good. But at least we tried, okay? So, no harm done. So this is the best circuit that we can get out of this, okay? When I give you guys these problems on the homework, I just ask for a circuit. I'm not asking you for the best circuit, okay? Your next teacher might ask you for the best circuit. That's when you use the Boolean rules. Okay. Questions I can answer, guys. Pretty easy stuff. Yes, sir, please.
So distribution wouldn't work at all because of the knot.
Correct, right. If for some reason I did this, which would turn into that, then you could factor out the P, okay? But it doesn't do that, unfortunately. So we're stuck with that ugly beast, okay? All right, other questions, guys, I can answer. Okay, nice and easy. I usually put something like this on the exam for 5 points, okay? So those would be 5 easy points for you guys. Okay. We haven't necessarily looked at the table and trying to get some sort of circuit from the table. Okay, so let's take a look at an example of that. So I have 2 different tables, and what I want to do is I want to construct, excuse me, I want to construct a Boolean circuit from the table. Okay. Now, I know what some of you guys are going to do. You're just going to Boolean it out, and you're going to figure out what permutation works, right? And that's fine for the first one. Might even be fine for the second one. But what happens when we get circuits that literally have like maybe 5 inputs? Oh, it ain't going to work anymore, right? There's only so far and so smart we can be, okay? Here's the way to approach it, guys. If it has an output of 0, don't care. Okay? So, whenever you guys are doing these problems with input-output tables, okay, why do I want an output of 0? Well, I'm not going to be able to construct something that has an output of 0. I'm going to, by default, get something that has a 0. What I'm going to focus on is I'm going to focus on the rows that have an output of 1. Okay? In computer programming or computer architecture, we call that a recognizer. Okay? So any column that has a 1, okay, that animal is called a recognizer. We don't care about the other rows. Okay? Like I said, this is not the most efficient circuit. Okay? So what somebody does is they make a circuit from what they have here, and then they might use some Boolean algebra to simplify it. Okay? So let's actually make the circuit. Okay? Notice I have 2 inputs. I have a P and a Q. Okay, actually, let me do this on the board, because it'll be ugly if I try. You guys can fit it in here, because you have a nice little pencil and pens. So I have a P and a Q. Notice the first input that has a recognizer. P is true and Q is false. So here's what I'm going to do. P is true, and I want Q to be false. So basically, if it has a 0, I'm just going to affix a knot to that. Okay? And think about it, guys. If I throw 1, 0 through this, 1, 0, that's going to end up being true, provided that these two are connected with what digital logic's circuit? Not an OR, but an AND, right? They have to both be true. Okay, so I'm going to connect these with an AND. Does that make sense, guys? And that's just for the first of the 2 rows.
Okay, Q is 0. Okay.
Correct. See how we have 1, 0, and all we're doing is just throwing the 1, 0.
Yeah.
Now, let's focus on the second row of the recognizer. Okay? All I'm going to do is I'm going to branch off of this. So here's my P. Here's my Q. Okay. Notice that both P and Q are 0s. So there's 2 different ways I could build this. Okay? One way is I could just put a knot on both of these. And then connect those with an AND. Okay, and that's perfectly fine. There's nothing wrong with that. Okay. Another way to do it, or maybe you guys can tell me, what's another way to be able to do that? Couldn't you just connect it with a big old knot? Okay, just like a huge knot would work too. Okay? But if we're just going through and trying to create a circuit, not the most efficient circuit, we would just put a knot on both of those.
I mean, you can, a knot only takes 1 input, right? So wouldn't you have to put an AND and then a single knot?
Well, when you do a knot implies AND as well. Okay, it's almost like a NAND if you do that. So a knot AND.
Oh, when you have 2 inputs into a knot.
Right. If you do this, okay, you can assume that's a NAND circuit if you would, not AND. Okay. So, but this is probably just more clear if we do it this way. Now there's one more thing that we have to do to finish this circuit off. Okay? Does anybody think they might know the last thing we have to do to finish this off and make it a correct circuit? Well, remember, digital logic circuits only have 1 output. This has 2 outputs right now. So we have to somehow connect these. We're going to connect it with, what was it, guys? An OR, correct? How come an OR, not an AND? Well, remember, as long as row 2 or row 4 is valid, you want an output. Okay, so when you guys are done, what you guys are going to do is connect it with an OR statement. Okay. If you wanted the most efficient circuit, what you guys might do is just construct a Boolean algebra expression for this, and then try to use the Boolean laws to simplify. Okay, I'm not asking you guys to do that. I'm just saying if you were to do that. Okay. Does this make sense, guys? Any questions? Not meant to be difficult. Sir?
You could just do not Q, couldn't you?
Yeah, in fact, if you were to express the Boolean, it would exactly work out to be not Q. Because what you notice is that the Q's are 0. Anytime the Q's are 0, the output's 1. In fact, if anybody wants to go through and verify that, you probably have to use De Morgan's law, then you have to use the distributive law, and then probably an absorption law to verify it. So did you just inspect that and know? Because you're just like, oh, that's easy to see. Yeah. And that's fine. If you can see it, that's great, okay? Like I said, with 2 inputs, most of you guys could probably bully it, okay? But like I said, if I start having 3, 4, 5 inputs, you're not going to bully it. It's going to bully you if you do that. Okay. So, other questions or comments so far? Okay. Why don't you guys try the second
Why
one?
did you add the or again at the end? Can you,
Why is there an or at the end?
Mhm.
Remember, this is a recognizer. We want the output to be 1 if this is valid or this row is valid. It doesn't matter which row is valid. It just matters that one of the 2 rows is valid. Okay? But why don't you do this? Why don't you run 1, 0 through, okay, and you'll see that it works. Run 0, 0 through, and you'll see that it works. Okay? But remember, you got to connect it with something. Okay? And if you did it with an and, well, there's no way to have these both true at the same time. It doesn't work. Okay? It's either one's true or the other one's false. Okay? It might be helpful, like I said, to run both of these through the circuit to justify to yourself that it works. Okay? So give that a try and see if that works. Okay? All right, guys. So go ahead and see if you guys can do the second example. Okay, I'll give you guys a few minutes to do it. It might look like an ugly circuit. That's okay. Do what you can with it. If anybody needs help, let me know so I can come over now.
Yeah, I'm not sure how to think about this.
Okay, so maybe the first thing you want to do is get rid of anything with an output of 0, right? So that way you're only focusing on rows that have an output of 1. So these are going to be the only 3 rows that you're worried about, right? There's 3 inputs, P, Q, and R. So, start with the P, start with the Q, and start with an R. And then from there, what you might want to do is just use the example we looked at before. If that has a 0 in that column or in that row, you just put a not gate on that. Okay? And you're going to have, I believe you're going to have 3 different, I'm going to call them like subsections of this, if you will, because there's 3 recognizers. Does that make sense, sir?
No, you are doing 2 operations on one of this logic, right? Like with AND, you're doing 2 operations.
Yes.
P and
And you only need 1 AND
okay.
to connect all 3 of them together. Because it could be P and Q and R at the same time.
Gotcha.
Okay? If you wanted to, you could make it 2, but you really only need 1. By the way, for those of you guys that are done, I don't know if there's a more simple circuit for this. There may or may not be, but if it is, it might be tough to find it. Yes, sir.
How many inputs can go into an AND?
You can do 3 for this. Okay, just do like a theoretical. You don't have to do like P and Q, and then another one that stems from that. Okay, so you can do more than that. Okay, because remember, we're just throwing it into like the I guess the logic component that makes it up. So yeah.
How much would you actually be able to do in like a real situation?
In a real situation, you'd actually have to do, if you're talking bare bones, you have to do P and Q first.
And
Then the output of that, you'd link up to an
then
AND.
R.
Yeah. But we're lazy. We'll just do 3 at a or efficient, I'm sorry. That's the government word for lazy.
Appropriate lazy.
Yeah, appropriately lazy, indeed.
For the second one, the 0, 1, 1, 1,
Mhm.
I have or connecting the P and the Q. How do I add this that?
Now, you shouldn't have an or until the very end. Everything should be an and until you get to the end of it.
Yeah, but still, I'll have one left over, so I could add the or, right?
At the very end, you should have the or, but you shouldn't have ors in between there anywhere. So, you might want to use a not instead. Alright, let me go through and show you guys like what I would do if I was constructing this circuit, okay? Obviously, there's 3 inputs. If there's 3 inputs, you should have 3 wires, if you would, running through those, okay? I look at the first line. P, Q, and R must be true. So what I'm going to do is I'm going to say P is true, Q is true, and R is true, and just connect those all with a big old and, okay? Technically, okay, and this is what the gentleman asked, what it should be, okay, is that we should have an and running through the PQ and then connect it with another and. I'm not worried about that, guys. Okay, so just do it all at one time. Does that make sense, guys, as to why that's going to be an and? It's because all 3 of the first line is true. For the second line, okay, now notice that the P is false. So what I'm going to do is I'm going to branch off of the P, and because the P is false, I'm going to put a not there. Okay, so as soon as I see a 0 in that row, I'm just going to put a not on that. Okay, it's the easiest way to do it. Not the most efficient, okay, but the easiest way. The Q and the R don't matter. Or they do matter, excuse me. But I don't have to make them a not. Okay, so what I'm going to do is I'm just going to conjoin these with another and. Okay. So Donnie, does that make sense as to why I'm not using an or there, sir? Okay. And then finally, I've noticed the last row with the recognizer has 0, 0, 1. Okay? There's 2 ways I can do this. I could branch directly off the P. Okay. Or, if I wanted to, I could put this after the not because the P is false. I'm just doing it as basic as I can. So notice the P has a 0 and the Q has a 0. Anytime we have a 0, we put a not there. Okay, so P has 0 and Q has 0, but R does not have 0. And then I'm going to conjoin these with an and. Okay. And I guess I should probably connect this. The last thing we're going to do is we're going to connect all 3 of those subcomponents into one big old circuit. So this, and this. And we get it. Because it's either the first one, or the 5th one, or the 7th one. Okay? There's no way they can happen at the same time. Okay? Yes, sir.
So, I know how you said you don't care whether or not we do P, Q, and R all in one big
Correct.
thing, but is that something that might matter later, varying from professor to professor?
It might, okay? So, I always try to give you guys the most efficient way of doing things, okay? You know how different teachers are. Like, you know, I mean, some of them, like, whenever I teach calculus, I don't make everyone write out every single limit law. Some of your teachers did do that, okay? So, it's just teacher to teacher, honestly. Okay, so, they might, okay? Sorry. Okay. Guys, any questions about being able to build a circuit if you're given the table? Yes, sir.
Just the process-wise, I'm trying to think through. So you do each one individually, and you ignore the other options, right? So you do it one line at a time, so then you look at, after that, you go to the next one, and you kind of forget the other one,
Yep.
so, okay.
Correct.
Because I was trying to, for some reason, I was like trying to combine to make sure it all made sense, and I was like, wait, that's probably not the right process.
And that's what we want to do. We want to try to think of things like collaboratively as opposed to independently. Okay? Yes, sir.
So when we're building these, we always want to combine them with ands and
That-
then finish with them.
Correct. And at the very end, you use the or. Okay? You never want to use an or in the middle here. Okay? Just at the very end. Because quite honestly, you need all these conditions. You need P to be false, Q to be true, and R to be true to get an output that's true, okay? But at the end, it's either row 1 is true, or row 5 is true, or row 7. It doesn't matter which one of them is true to get a 1 as the output.
So after you draw the circuit, I know you ignored anything that had the output of a 1 when you're drawing it, but should those also work after you finish it?
Yes, sir. So if I ran, let's say I ran a 0, 0, 0 through, I should get a 0 as the output, right? So let's try it, okay?
I was trying to 0, 1, 0.
Or 0, 1, 0?
I was trying something it wasn't. I was trying 1, 0, 1.
Okay, let's try it. So 1, 0, 1, 1, 0, 1, 1, 0, 1. Okay. Alright, so check this out. 1, 0, 1 through an AND is a 0. As soon as you have that. Okay? 1, 0, 1. This makes 0, 0, 1.
Right.
That's a 0. And then right here, 1 going through a NOT is a 0. 1, 1. As soon as you see 1, 0, that's a 0. 0 or 0 or 0 gives you an output of 0. Okay? So maybe you just made a copier or something like that. Whatever it is.
No, I was, for whatever reason, right as you got to the end, I realized I was trying to make it become a 1.
Oh, okay. Right.
That's why I'm like,
That's okay. Yeah. And guys, if you want to, go home and try the other 4 to justify to yourself, okay? I mean, a lot of this, like, you're just taking for granted that I'm saying it works. Go home and validate it for yourself, okay? It'll literally take you guys about 4 or 5 minutes to do all of them, just to verify for yourself that it does work, okay? I mean, you could believe me or not believe me, but again, just make sure for yourself that you believe me. Okay. All right, guys. So the next thing I want to do is, if I give you guys a circuit, okay, or if I give you an expression, you should be able to construct a circuit. Okay, these are actually fairly easy problems. They're just like order of operations problems. You start inside and you just grow your circuit. Okay, so this is almost the opposite as what we did earlier. Okay, so let's go ahead and try to construct them over here. By the way, it doesn't matter what order you put the circuits in. Okay, so I have P and not Q. So here's what I'm going to do. I'm going to have a P, I'm going to have a Q. Remember, NOTs are higher precedent than ANDs. So this is literally what I'm going to do. I'm going to have a P and not Q. That's it. Okay, so that's just for the first parenthesis. Then order of operations says I do what's in the second parenthesis, right? So I'm not going to worry about this or until the very end because it's outside the order of operations scope. I have a not P, so I'm going to branch off of this P that I have already. I'm going to make it a not. And then I'm going to introduce a new wire, which I'm going to call R. Okay. Those are supposed to be connected with a logic gate of OR. So now what happens is, I have both of my parentheses done. Inside the parentheses, I follow the order of operations. The last thing I notice is that I have an OR that's going to connect those. So I've gone in the parentheses, now I can connect the OR. So this might be one possible circuit. Not saying it's the only one. Okay. But this is one possible circuit that would represent that Boolean expression. Okay? So, like I said, guys, think of them like order of operations problems. Start in the parentheses and just grow your circuit out based on the order of operations. Parentheses, and then NOTs, ANDs and ORs, and then implies. Although we're not going to do any implies with this stuff. Okay? All right. So, guys, why don't you try the second one, just to make sure you guys get a little bit of practice doing this stuff. Start with the innermost parentheses, grow your circuit out. Okay? It doesn't matter what order the inputs go in. So you don't have to have Q second and T last. Okay, you can have Q first and T second. Doesn't matter.
T being a variable.
Correct. T is a variable, not a tautology, and I promised that I wouldn't do that again. So the moral of the story is you can totally not trust me, right? Okay. Not T is contradiction. The only reason I did that was because I've had this made up for 10 years.
Yeah, that's fine.
Sorry.
Why is that one or in the middle not like in the, like it's not in the thing?
Order of operations. Okay. Order of operations, just like regular arithmetic, says you do what's in parentheses first, right?
Yeah.
So I constructed P and not Q first. After that, I constructed not P or R. And then because this is on the outside of parentheses, I did that last. So the last thing, or the rightmost operation, is the OR, okay?
Oh, the or, oh, okay,
Right, this OR is the
The
one
OR
that's on
at the
the
end.
outside. Right. Okay, does that make sense, sir?
yeah.
Okay, good. Yeah, I think, okay, I get it now. You were just mixing up ORs when you were doing it. Yeah, the OR on the outside, or in between those, is the one that's the rightmost OR. And by the way, your circuit might look different than somebody else's, like if you're collaborating with someone, doesn't mean it's wrong. Doesn't mean it's right either, okay? But different doesn't mean wrong. At least that's what Mom told me.
Oh, you found her to be.
What's that?
Have you found that statement from a teacher?
Absolutely not.
It's cleaner when you say it.
It got me beat up a lot. Unfortunately. Let me give you guys another minute to try to get this together, and then we'll go through the answer, or a possible answer to that. Excuse me.
You were right the first time.
What's that?
You were right the first time.
Oh.
The answer.
Okay, the answer. Well, it's the one that I prefer to grade because it's going to be this easy.
So do we have to put our letters in like that same order?
No, you can do whatever you want. The only reason I did it was because that's the order they present things.
When we're drawing the circuit, if we get the shape correctly, do we have to put the end and all in it, or is it just the shape?
Just the shape, that's fine.
And, thinking about the test.
Correct, yeah. I understand that there are literally an infinite number of permutations that you guys could develop for this, okay? I'm asking you to please be kind when you're doing it, because there's 25 of you and 1 of me. So when you guys are designing these, it's a little bit of a pain in the ass for me to grade these, so try to be nice if you can. Try to make your wires straight and not like roller coaster loops or anything like that. I might just take off a point for you being a prick if you do that. I'll actually write prick point on it. Alright, so one possible circuit, here's the way I'm thinking about it, okay? I'm looking at the leftmost inner parenthesis, not Q or T. So, or is that, there's an in, okay? So, and then I notice that the next possible would be not P or R. So I have a not P or R. Now, inside of the parentheses, I notice that there's an and between those two parentheses. So what I'm going to do is I'm just going to connect those with an and to make it nice and easy. Okay, not saying that this is the way you have to do it. This just might be the easiest way. So what that does right there, that takes care of the leftmost inner parentheses. Okay. Last thing I have to do, I just have to make a circuit for P or not T. So I have a P, and I have a T. So here's my T. It's going to get connected with a not. Then I have a P. It says or, so it's going to be P or not T. And then the last thing I notice is that completely outside of any parentheses is this or. So by order of operations, I would just connect these with an or. Okay? And like I said, this is one of an infinite number of possible circuits that you could construct, okay? I'm gonna guess several of you guys had, go ahead, sir.
It's nice to see your oars don't look any better than mine.
Oh, no, mine are horrific, okay? Yeah, and I apologize, you know, I've been doing this for years, and it's actually looking worse than when I started, so, sorry about that, so. So I guess by the time I'm like ready to retire, they're just, all my gates are gonna look exactly the same, so, sorry about that. Okay, guys, any questions I can answer about constructing a logic circuit given the Boolean statement? Okay, not too difficult. Okay, last thing I wanna look at, before, with Boolean circuits is, if I give you two circuits, how do I know that they're the same, or how do I know they're different? Okay, there's actually two ways that you can do this, okay? So, Boolean circuits are equivalent, and maybe you guys can help me out and answer this, okay? What's one way that I can tell that two Boolean circuits are logically equivalent to one another? Done?
Putting zeros and ones in them.
So basically, input-output table is the same, right? I mean, if they do the same thing, they're logically equivalent. They are not equivalent, they are logically equivalent, okay? So, let me put the word in here that they are logically, oh, shoot. Thanks, technology. Oh, that's even better. Never mind, thanks, technology. So they are logically equivalent. So one way to do this is to do the in-out tables. Okay, I like that. Does anyone else have another way that we might be able to decipher this?
Simplify them with Boolean algebra.
We could make a Boolean statement and simplify them both, right? It's a little bit more painful, but it might be quicker depending upon what we're looking for. Okay, so they have the same simplified Boolean statement. Okay. So two different ways that you guys can determine if two circuits are logically equivalent to one another. Okay, you can make an input-output table, or you could just design the Boolean circuit, and you can see that they work out the same. Okay, the first of these two is extremely easy to do that with. Okay, so let's do that, guys. Let's just make an input-output table, and then I can make a Boolean circuit and for both of those, and I'll show you that they both work out the same. Okay, so from the input-output table, so we have 1, 1, 0, 0, 1, 0, 1, 0. And I'm going to call this one circuit 1 and circuit 2. Let's just call this one C1. Let's call that guy C2. Okay. All right. I bet you everyone in here can probably figure out the input-output table just by virtual inspection. Okay. In fact, when I was taking linear algebra, my teacher said one of the most dangerous things you can put is by inspection as a justification for a step, because then you can just put everything by inspection, even if you have no idea what you're doing with it. So I don't accept by inspection as a justification. All right, but regardless. All right, let's say I throw 1, 1 through this gate. I get a 0. And as soon as I get a 0, guys, through either of them, what do I know about the complete output?
0.
It's 0, right? So it looks like that 1, 1 for circuit 1 gives me a 0. What happens, guys, with 1, 0? It's a 0 as well, right? Because think about it. If I throw a 1 through the NOT gate, it becomes a 0. And anytime you have a 0 with an AND, you're done. Okay? Does the same thing happen with 0, 1?
Yep.
Yep. So we're hoping that if 0, 0 doesn't work, then we just got basically have a worthless circuit, and we just give it to our local congressman, because it's worthless as they are. So 0, 0. The good news is, though, guys, that when we put 0, 0 through the gate, 0 becomes a 1, 0 becomes a 1. So indeed, we finally get a 1 out of it.
You would want to give that to the congressman, because then they put 2 congressmen and say they got something good.
Right, and then they overspend on it anyway, and you know, it's just a big cluster F, so we don't want that. Okay. What about circuit 2, guys? Let's see if circuit 2 does the exact same behavior, okay? So, if I throw a 1, 1 through this gate, 1 or 1 is a 1, I negate a 1, it becomes a 0. In fact, doesn't it look like that whenever I throw a 1, anything that has a 1 through the OR, it's a 1, and then it becomes a negation, which is a 0. So I know 1, 0 becomes a 0. I know that 0, 1 becomes a 0. And then finally, when I throw 0, 0 through there, 0 or 0 is a 0. When I negate that, that's a 1. Guys, I want you to notice that the input-output tables for circuit 1 and circuit 2 are exactly the same, which means they are logically equivalent. Okay, so you would say, yes, logically equivalent. Okay. Yes, sir.
So if you were to set up Boolean statements for the two.
Okay, so you would have not P and not Q, right?
Yeah, P, Q,
Okay. For circuit 1. For circuit 2, we would have not P or Q, correct?
No, P or Q, yeah, not P or Q.
Not P, because the not comes after, and then the or comes before.
So when you set this up, can you use the basic rules of inference?
Sure, or not the basic rules of inference, but the Boolean
So
laws.
you can't use the basic rules of inference?
Correct, because those are for argument forms,
Okay.
not for statement forms. Okay, so just one word difference, but unfortunately it does. Okay, guys, isn't it true that if you use De Morgan's law on either of these, it would give you the other one, right? So I could go ahead and use De Morgan's, and that would be not P and not Q, which is exactly the same statement. Okay, I don't care. Go ahead, Andre.
So, which one is the better one to use?
Ah, that's a good question.
Does it depend on the size of it?
Oh, it's all about size, isn't it? No matter what, it always comes down to size. I meant that in a perverse manner, by the way. Just in case you didn't-
I got it.
Oh, okay, good. So, take a look at the next one, okay? Now, think about trying to make a simplified Boolean statement for that one, okay? That would be ugly, right, guys? And I like what you're going at, okay? The bigger the circuit, the more complex this animal's going to get, which means we have to use more brain power, okay? We can either bully it or we can finesse it, one of the two, right? We prefer to finesse it, but, you know, if it comes down to time versus brain power, a lot of times we pick time over that. So, I'm not going to say that one's better in any instance, depending upon what you're better at, maybe, okay? I don't know if that answers your question or not. Okay, good. Okay. So let's go ahead and finish this guy off, and then we can be done for today. So we have a P, we have a Q. I'm going to call the monster circuit C1, and I'm going to call the baby circuit C2. Okay. Clearly, we'd rather work with C2. Okay. So let's just devise an input-output table for this. So we have circuit 1. Let me give you guys a suggestion, okay? Because I don't know if these are true or not, but why don't we start with the easier circuit? Because that way if we're running through the harder circuit and we get one that doesn't work, we haven't done all the hard work first, right guys? Doesn't that make sense, guys? Always knock out the easy stuff, and then if you get a contradiction between the outputs, then you just be like, oh, okay, it's wrong. I don't have to do the harder stuff, okay? So if I do C2 first, okay? As long as P is a 1, the output's a 0, or the output's a 1 as well. Okay, so I would get 1, 1 for the first two. Okay. Now, the only time that this is going to be a 0 is if Q is a 1. Because if this is 0 and this is 1, I would get 0, 0 through this. So I think the only one that would give me a 0 is going to be 0, 1. Okay. So, does that make sense for circuit 2, guys? Go ahead, sir.
Question, does the symbol, the little dot right after the not mean anything?
Oh, no. I copied it from somewhere. Maybe not legally, but the dot just means, just ignore the dot there. Okay? I've seen it written with and without the dot. Okay? I just don't do it because it's a pain in the ass. Okay. Alright, guys. Let's see if this circuit's true. Okay? In fact, might it not be easier just to go one by one on these? What's the only time that this first component is true?
When both are true.
1, 1, right?
Mm-hmm.
Any other time, forget it. Okay? So 1, 1 gives us a 1. Okay? What is the only time that the second component is true? When the first one's a 1 and the second one is a
0.
0. Doesn't that make sense, guys? So 1, 0 gives us a 1. And then finally, what's the only time that this last component is going to be true?
Both are zeros.
If they're both zeros, right? And then that by default means 0. The difference is, remember the method that we used before, where we just worked from left to right and we just built the circuit? Like if I gave you this table, all right? If C1 is the result of the method I showed you, C2 is the result of you trying to brain power, if you would, okay? So that's the difference between those two, okay? And obviously, we would say yes, they are logically equivalent because the tables are the same. Okay, so, yes, logically equivalent. Okay. So, any questions I can answer for you guys about the Boolean logic stuff? Okay? Sir, please.
You're saying yes, logically equivalent when you set something like valid by input output.
Oh yeah, sure. I think the question, I guess it just matters about what the question asks. It says determine if they are. So yeah, you could say valid by input output table. That'd be perfectly fine. As long as you answer the question, give me some substitute answer. Okay? Other questions, guys, I can answer. Okay.
So,
go ahead, sir.
if you were to write it on a Boolean algebra type, would like P, the circuit one, P and Q, then
Oh,
P
boy.
and not Q, and not P, not Q, and you have to add all of them to an OR sign.
Correct. Or between all of them.
Also,
And then have fun with that. That's
Okay.
just ugly. Okay. Other questions, guys? Okay. So for next Wednesday, I'm going to ask that you guys complete assignment 2. Okay. You can do anything with Boolean logic circuits on assignment 2. So maybe over the weekend work on those. And then the rest of the stuff concerning the number bases in the 8-bit edition, we're going to do that on Monday next week. But assignment number 2, that's going to be due on, I think we said what, the 14th? Okay. And then also, remember those last 2 questions with the logical, with the argument forms? Those will also be due. Okay, so assignment 1. I think it was problem number 11.
Yeah.
Was that it? Okay, so 11A and 11B. Okay. All right. I do have your guys assigned. Oh no, I don't. I got the first one, so that's fine. I'll have those graded for you guys by Monday. But remember, I post everything in Blackboard, so if you want to know your grade, I'll also post the solutions for you guys as well, so you can look through those. Okay. All right. So I will see you guys Monday. Have a splendid rest of the week.